All right. So, as you can see from the problem statement here, we just want to find the reactions on this particular structure. The drawing here indicates that this connection is going to be a pin connection. How many unknowns at a pin? Two. And then over here, the little round roller, that indicates it's a roller. So that's going to be a 1 reaction. So what I like to do first is just draw the free body diagram for the structure. So I'll redraw a line for the geometry of the structure. And then now I'm going to make some assumptions. So I'm going to go to A, and I'm going to assume that I have a reaction force up. I'll call that AY. And a reaction force to the right, I'm going to call that AX. Just assuming. And then over here for B, I'm going to assume that I have a reaction at B that it's also up. I'll label that BY. Now, I've got an applied load here, which falls right in the middle. I'll just bring that back down. That has a 24 kilonewton force, and that's right in the middle, so that dimension is 6 meters and 6 meters. Now, for the distributed load, it's really inconvenient to work with these functions, these loads, so it's always best to take a concentrated equivalent load of that. And the easiest thing to think about is when you do it is you just want the area under the curve is the force, and the force acts through the centroid of the area. So this is an easy area. This area is a rectangle. Every rectangle is base, in this case, which is 3 meters, times height, which in this case is 2 kilonewtons per meter. So 2 times 3 is 6. So I've got an equivalent force of 6 kilonewtons, and it acts in the centroid of this area, which is half the distance for a rectangle. So that would be a distance of 1.5 meters. So from my perspective, that's a pretty clean free body diagram. I've established my unknowns, AY, AX, BY. I've handled all my loads, and I've made an arrangement for this concentrated equivalent. Now, in this class, what I'll try to do is I'll try to use a double line here to indicate that that's an equivalent load. That's not the actual load. But for statics, it's equivalent to the distributed effect. Okay, so far so good? So like I mentioned before, the first step is probably going to be to sum moments. Where's a good place to sum moments? Yeah, A would be a good place because it's a pin. In this particular geometry, you can also do it at B. Why? Yeah, AX and BY are also concurrent at that point. So either one would work. I'll do it alphabetically, so I'll go to A. So the first thing I do is I assume the direction for my moment. So I use right-hand rule. So I assume counterclockwise is a positive moment. You can choose any way you like, but I'm going to do that the whole semester, so you'll probably get used to seeing it. So assuming right-hand rule for my sign convention, I'm going to come back now and sum moments at A and set it equal to 0. So it's a pretty powerful little statement there. All the moments about A should be equal to 0. So let's account for them. So looking at A, let's do the loads first. Both these loads are going to create what kind of moment with my sign convention? Positive or negative? Negative. So remember, moment is force times distance. So I'll take the first one here. So the negative sign comes to the fact it's negative moment. The force is 24 kilonewtons. And the moment arm, the distance from A to that force is 6 meters. So there's the moment effect about A of the 24 kilonewton force. So I'll just bump it up and do it again for the 6 kilonewton, the equivalent force. It's also negative. The force is 6 kilonewtons. That's the force. What's the distance? Well, that's 6 plus 6. And that little distance, I didn't write it in there, but it's 1.5. So that'll be 13.5 meters. So now I've accounted for the moment of the applied forces. And now I want to look at the kind of the resultant moment created by by. What kind of moment does that create with my sign convention? Positive. So I'm going to say positive moment, force by, and what's its moment arm, the distance from A to B?
13.
No? 12. So I've got one equation and one unknown, by. So what is by? Somebody out there calculate that for me.
18.75.
I'm sorry, I didn't hear you.
18.75.
Anybody else get 18.75?
Yes.
Excellent. I got a positive result for my value. What does that mean? by is acting up. Does that make sense? I think so. So also you probably already started developing a little intuition in statics. We're going to continue to rely on that in this course to kind of give you some feedback that you're moving in the right direction. Now what do I do? Could I sum moments again? Yes. I could sum moments at B and find AY. How else can you find AY? Sum forces in the Y. That's probably going to be an easier equation. Summing forces is usually easier than moments, so we'll go that way. So in that case, I'll assume that up is positive, and I'm going to sum all the forces in the Y direction. So I've got AY up plus BY is up. What else do I have? 24 is down, so that's negative. And 6 is down. That's also negative. Oh. All I have to do now is just plug that BY right into there and solve for AY. And you probably get like 11.25. Also positive, so again, I assumed AY is up, and it is. So far, so good. So we're only left with one. This is kind of trivial right now, but it won't be in the future. We will get some components there. So I always like to assume right to the right is positive. So now I'm going to sum forces in the x direction and make sure they're 0. And I look at my x components, and I just have AX in the positive direction, but it doesn't really matter. One equation, pretty easy to solve. AX is 0. Sweet, huh? You'd really like it if you got that problem on the test, wouldn't you? Yeah, probably will. Okay, any questions about that one?